Good morning, everyone. Thank you for coming to Psithon on the Developers Day. I'm going to talk to you a bit about Psithon, PsiAPI, and QCSchema. These are words that we throw around a lot, and there are more ways than ever in order to run your Psi4 calculations and get data out of them. So I thought that I would review what these mean and some of the ones that you might not have been aware of. Okay, this is a Model Jupyter extension that lets you do both presentations and running code. So we have Psi4 and a few other packages loaded. And I'd first like to talk to you about this figure that you may have seen before. This is a comparison of three modes of input for Psi4. The traditional Psithon, which is a text file with some markup language. Anytime you see a curly bracket, then you're dealing with Psithon. This requires fewer characters, fewer quotation marks, and for a long time was the only way of running an input in Psi4. To execute it, you would simply take this input file and run it in Psi4. Since 2016, we've also had PsiAPI, which is actually a Python input. You import Psi4. You express the geometry like so, with the content looks exactly like Psithon. In order to set options, instead of being able to ignore all of your quotes, you instead have to actually quote strings. And then you would run Psi4 energy call. Note that you have to put a Psi4 dot in front of many of these calls or in order to properly namespace. These are exactly the same. And you would generally run it by saying Python input file. Although you can also run this through Psi4 and just say Psi4 input file. Finally, most recently, this is QCSchema. This is simply a Python dictionary. We have a molecule. This is the same molecule expressed here. Note that whereas in Psithon and PsiAPI, you can use Z matrices, you can use angstroms, deferred evaluation. In QCSchema, it only stores things in Bohr, and it only stores things in Cartesians. So you would have to make this translation. Apart from that, driver to this is energy. We express the method and basis in this model section, and any keywords you express here. And this you would generally run as Psi4 minus QCSchema, and then this input. So as I've said, Psithon is a special character-reducing syntax. It has Psi4 pre-imported, so you can just use a lot of commands right off. It runs through a preprocessor. However, this comes at the cost of a domain-specific language that someone has to learn. And the only way to run it is Psi4. To actually see what this looks like, we can write the file, and then we can run it. So this is simply running Psi4 Psithon, and reading the file, you get the familiar output that you're PsiAPI is pure Python API. You're going to need to mind your strings and views and quotes. Commands are going to need Psi4. And some of the convenience functions replace that special syntax for molecule and option. There's many more ways to run this. You can run it through Python, you can run it through Psi4, or the most usual way is actually doing it in a Python. See what this looks like. We can write this file out and run it, and all the results come directly to screen, and it's the output file that you're all using. Finally, QCSchema. This is the most format that exists for a molecule basis set in QC input and output. It has a definition, it has a reference implementation. And though we often see things in JSON, it also can emit things in message pack so that you don't lose a binary accuracy. It can't do absolutely everything that Psithon and PsiAPI can do, but 99% of what you wish is available for PsiAPI. To run it, you can either run it directly in Psi4, or you can use it in a Python session by simply running the Psi4 command with your input. Or in a Python session, you can import QC engine and call QC compute on your input, and then also specify Psi4 as the second argument. All these are covered. See what it looks like. You write this file and then run Psi4 minus QCSchema. And so here we get back something a little different. We have the input schema repeated. Driver is energy. Extras contains the QC bars that we all know and love. The keywords are reported. The molecule is reported. Some other properties are presented. And finally, standard out. This contains the actual output file that you are familiar with. So you haven't actually lost any information by running things this way. It's also a success. So to see how all these pieces sort of go together, Psithon and PsiAPI, they use, of course, Psi4.core.molecule, which is very flexible. QCSchema uses the PC elemental molecule, which is less flexible, but its creation is flexible. You can create molecules from strings in all these methods. You can create molecules from data. So if you simply have your geometry and you know your elements, then you can get forming those into a string and form them directly through the from arrays object. Do the same thing for QCSchema. You get a molecule out of that. And of course, you can go between all of these modes. So if you have a Psi4 molecule, you can convert it to schema and load that into the QCSchema molecule and get out your QCSchema molecule. And of course, you can go in the reverse direction too, from a Psi molecule to. Of course, both of these are loadable. You can get the geometry out. Of course, everything from Psi4 comes out in a Psi4.matrix. But thanks to the NumPy array syntax that Windows with implemented, you can just do .np and get out a NumPy array. On the QCSchema molecule, do the same thing, just do the .geometry. Get out masses and symbols. For Psi4, you can use the Psi4 API directly and simply iterate over all the atoms and store the mass in an array, or store its symbol in an array. Those are these first two lines here. Or you can convert it to a dictionary and then print out those fields. So these are the same. For QCSchema, likewise, you can call the .masses or the .symbols in order to extract all this information. QC variables are what were formerly known as Psi Variables. They're simply carefully named pieces of results. And now they work for arrays as well as scalars, usually in atomic units. Originally, they were all stored in globals, but we are moving them over, and so that they tend to largely be stored on wave function, part of the shift away from globals. So QC variables in PsiAPI, we're going to make a call, CCSD calculation on this molecule, and say to return the wave function. And then this is going to print out the variables from globals. So this is going to contain the coupled cluster total energy and then a number of components for it. It's going to map some of those to the current labels. And because you get MP2 along the course of it, then you can also have all these MP2 data and also SCF data. You'll notice here there's an SCF dipole that is an array variable. Okay. You can also grab these things directly from the wave function. So here we're calling wave function.variable and getting out a specific one, the CCSD total energy, or getting out the dictionary of all of them. I'll throw in a little interjection for QC elemental for unit conversion. This datum is a way of associating a label and a unit and a piece of data, be it array or scalar. And then we can, so this has been put in or squared, and then we just asked it to convert to units of Debye angstrom, and it obliges. Getting QC variables out from QCschema, the QC vars that you're familiar with are stashed in extras, but QCschema also provides another field of specially named properties, and many of Psi's outputs are translated into that QCschema properties. To see what this looks like, we can take an atomic input of the QCschema molecule, do an energy calculation, that is again a CCSD, CCPVDZ, setting this particular keyword of reference UHF, and then forming this into an atomic input and printing this out. This is a pydantic object, which you don't have to know too much about, other than it's a way of strictly controlling a dictionary. And when it is in its object form, in order to look at it as a normal dictionary, you just have to call this .dict on it, like we do here in order to print it. This is what the input for a calculation looks like. Keywords, model, and molecule. And to see what it actually looks like when it's running it, I'm going to call QC engine compute on it. I'm going to take that atomic input, request that it be run in Psi4, and request in particular these local options of a kappa gig of memory and 2 cores. And this is going to return an atomic result, which we will again print. Okay. So here we get our results back. And as I said, the QC vars are all stored in extras, sort of a free-form field that you can put things in. And then properties contain some of the QC vars like objects. So the number of molecular orbitals, the CCSD total energy, and so forth. So QC vars is going to be more populated because the QCschema properties are still being built out. In order to extract things directly out of the atomic result, simply call extras, and then because it's a dictionary, QC vars CCSD total energy. That provides one number, and if we've done this translation right in the code, then calling atomic result properties CCSD total energy is going to provide the same number. Sort of 2 different places that everything are stored. One of the newest additions.
Morning. Yeah,
Hi.
that's good.
Okay. One of the newest things is
there
wave
are
function results. Been able to return wave function for a long time, since in Psi4, since early 2016. Another work we're doing this with. But now we can actually store some of these in QCschema, particularly in the CCA format, and this is SCF only at present. So if we took our wave function, we could get out orbital energies simply by calling epsilon A and converting it to numpy. Or we could get out the orbitals themselves. So this is PsiAPI. Whereas in QCschema, you would take your atomic input, and then wave function results are somewhat heavy, and so you have to particularly request them. And the way that we do that is to add this protocols wave function. Anything in protocols is a way of shaping the data that the result gives out. So we request orbitals and eigenvalues, and so that has added this little field. This comes about because I'm writing on top of this, and I've executed one cell too many times. It really does this. I imagine this won't look either. Oh, it does. Okay. Anyway, we actually run this calculation, and then on the atomic result, taking the wave function field, we can print out these eigenvalues and the alpha eigenvectors. And these won't match exactly what's coming out of wave function because they've been translated into CCA ordering. So when to use each of these? For Psithon, if you have a new user that you're introducing to Psi4 and who doesn't know any Python syntax and will never need to know any Python syntax, then Psithon is great. For users running independent individual jobs and you have to write out the output by hand, the input by hand, again, Psithon is great. And this is what most of the test suite is in. QCSchema, on the other hand, is really great for machines reformulating, running, and harvesting jobs, or for users running non-interactive and independent jobs through Python. And these, of course, are still tested, but not quite the breadth of a test. PsiAPI is pretty much everyone else, because at the cost of a few more quotes and Psi4 dots, you can avoid the domain-specific language and actually be using Python directly. And these also have their own extensive test suite.